So you may have heard the news of the Transiting Planets and Planetesimal Small Telescope, or TRAPPIST, which has discovered an ultra-cool dwarf star surrounded by 7 exoplanets, 3 of which are found within the so-called Goldilocks zone, which means that, like the oats of Little Bear, they are neither too hot nor too cold, such that water could be found in its liquid state, making us hopeful about the prospect of finding life, which is oddly befitting of the constellation this exoplanet system was found in, Aquarius. Because these exoplanets transit, which means they pass in between the star TRAPPIST-1 and Earth, scientists have been able to find out a fair amount about their size, their orbits, and maybe even enough to make some inferences about their composition. But there is still a lot left to be researched to determine how habitable they really are. So today I thought my friend Josie and I could teleport over to the TRAPPIST system and find out for ourselves. So let's go! Hey, we made it! We're on TRAPPIST-f, and it's one of the outermost exoplanets of the 3 exoplanets which orbit within the Goldilocks zone. And the first thing I'm going to do is to get ready to celebrate my 937th birthday, which, as you'll discover in a future video, is a pretty cool number.
The reason our birthdays have suddenly shot up is because we're very close to our star TRAPPIST-1, and 1 year over here is equivalent to around 9 Earth days. We'll have also aged a little bit faster too, because the gravity is weaker both for our star and the planet we're on. Weaker gravity makes time actually go faster. Thanks, general relativity. No face cream is going to fix this. But we are closer to the star, so it won't be so bad, and having a birthday every 9 days should be fun. However, that doesn't mean that day and night go by quickly. In fact, it's quite the opposite. Where we are right now, on the side facing our TRAPPIST-1 star, it is permanently daytime.
At the distance we are from the star, our planet has become tidally locked, just like our moon back on Earth. The same face always faces the star, and the same other face always faces the rest of the universe. In fact, that's pretty bad news, because there's a very high chance that the other side of our planet could be frozen, and if it freezes such that the atmosphere collapses, well, I guess that's goodbye.
But hopefully there's enough carbon dioxide in the atmosphere to keep it going. This is also the reason for the hostile winds we receive, due to the significant differences in pressure and temperature across the different sides of the planet. I imagine this could make it quite hard for life as we know it back on Earth to adapt over here, as there would be no visual cues for our biological clocks to use to adjust to a day-night cycle over here.
On the other hand, if any of these exoplanets turns out to have any moons that could suitably harbour life, they could be a wonderful alternative, because they would be tidally locked to their planet, which would provide a day and night overall as they orbit the main star. On the topic of light, you may have heard that due to its size and surface temperature, TRAPPIST-1 is 200 times dimmer than the Sun, and although we are much closer to it than the Earth is to the Sun, because the spectrum of light emitted is much redder beyond the visible spectrum, you may want to crack out the infrared cameras to see us better. In fact, any organism with a visual system would need to shift their photoreceptor sensitivity towards the infrared spectrum to see as well as possible, although they will probably want to retain some sensitivity towards the opposite end of the spectrum to shelter themselves during the frequent stellar flares.
Stellar flares could be a big problem. A stellar flare is a sudden flash of brightness near the star's surface, with enough energy in particularly big stellar flares to be the equivalent of 1 billion megatons of dynamite. This emits a lot of X-ray and ultraviolet radiation, which we know is harmful to organisms on Earth. We have a protective magnetic field and atmosphere on Earth, but frequent energetic stellar flares can erode away atmospheres around a planet. Different types of stars emit more stellar flares than others. Red dwarfs are renowned for being very active, and young stars are too, of which TRAPPIST-1 is both. TRAPPIST-1 is a red dwarf and it's only 10th the age of the Sun, 500 million years. So it looks like it could be stellar flares and storms aplenty, though there is hope with recent measurements that show it to be a little less dramatic than expected. Maybe the planets have held on to their atmospheres. An ozone layer would be essential to deflect as much of that radiation from reaching the surface of the planet.
Honestly, the absence of an ozone layer would not bode well for any potential life forms, and would suggest that life would need to originate sheltered from such radiation, such as within caves or underwater. And something that we know about TRAPPIST-f, the planet we're on, is that it has by far the lowest density of all of the exoplanets. We know that it isn't a gassy planet, which leaves us with several other possibilities. One is that it could be composed of mostly water, so we could possibly be underwater right now. This may not be all that bad though, because life did originally originate in the water on Earth, and it would shield early life from the malignant effects of the UV radiation from stellar flares. But if there is too much water, there is the chance that the increased pressure of the water could have turned the bottom layer of the ocean into ice, and that would certainly not be conducive to life at all.
Alternatively, TRAPPIST-f and the other low-density exoplanets could be just rocky as expected, but have fewer heavy metals in their core. Planets need heavy metals and convection currents in their core to create an electromagnetic field, and this is what holds onto and protects a planet's atmosphere. Whilst the gravitational pull from the nearby exoplanets could lead to tidal heating and help an electromagnetic field become established, at such a low density it could be too weak to maintain an atmosphere. And without an atmosphere, the establishment of life here would be complicated.
So could life here develop at all? I mean, so far the current state of the planet seems a little bit grim. The other thing is that it seems likely that this TRAPPIST system is still quite young, and bearing in mind unicellular life took its time to appear back on Earth, and far, far longer to become multicellular and complex, let alone intelligent, and under ideal conditions life may not even have had time to originate over here yet.
We did point SETI, the search for extraterrestrial intelligence, over here, and we didn't find anything. So there probably isn't anything here, honestly, apart from ourselves, which, by the way, I'm starting to feel a bit odd out here.
Yeah, perhaps we received a little bit too much radiation, or perhaps not enough oxygen. Either way, I think it might be time for us to go back. Whew! Well, that was quite the trip. Hopefully you enjoyed today's episode. Of course, a lot of what we've spoken about today is certainly speculative biology because there's a lot left to be discovered about these exoplanets, but I'd be really interested in hearing whether you think any of these planets could be habitable, and perhaps more generally, whether we will ever find alien life on another planet. I've also got a lot of people I want to thank in this episode. Josie Peters and Amy Hong, both of them have incredible YouTube channels, and they both helped collaborate with me and put this episode together at really short notice. And also to Dark Sapiens, Amy Seals, Alex from Efecto Xalamito, Nahúm Chazarra, Villatoro, and Josie Peters, because all of them answered a barrage of questions that I had about the TRAPPIST system, and you can find all of their various science communication endeavours and links on screen and in the description below. And as always, thank you so much for watching me, and I'll see you in the next one.